Good morning, everyone. It's great to be here. Welcome to Lost in Transaction Process Doppelganging. My name is Tal Lieberman, and I'm the Security Research Team Leader at Ensilo. With me here is Eugene.
Hello, I'm Eugene Kogan, software developer from Ensilo.
And today we're going to be talking about Doppelgänging, which is a new evasion technique for Windows. And we're going to start off by talking about the history of evasion techniques. We're going to move on to talk about AV scanners and all the different factors to consider when implementing one. Then we're going to discuss transacted NTFS or TXF, as it's known by Microsoft, and then move on to discuss the evolution of the Windows process loader over the years. Finally, we're going to get to the Doppelgänging execution flow, followed by a live demo. And then if we have time, we'll discuss a mitigation in Redstone, a story of a blue screen of death that we ran into while conducting this research. So advanced code injection techniques and evasion techniques have been with us for many years now. Notable methods are ghostwriting, atom bombing, power loading, propagating, which was only recently released a few weeks ago. We have reflective loading, which is loading of DLL files into memory without ever placing them on disk. And we have process hollowing, which is basically running a malicious process inside of a container process. So let's take a look at a bunch of these. We'll start off with ghostwriting. This, as the author describes it, is a paradox, writing to another process without opening it nor actually writing to it. And it's an injection technique from actually over a decade ago, from April of 2010. And it hasn't really received much attention, so it's why I decided to cover it in this talk. The goal here is to inject arbitrary code into a process, in this example specifically explorer.exe, and do that without opening the process, without writing to the process's memory, without creating any threads in the process, or using APCs and whatever. Now this technique works by first finding two patterns in NTDLL. We're going to call them the move pattern and the jump pattern. Now, we're going to use these two patterns to achieve what we call a write what where, which is basically the ability to write whatever we want into the target process's address space and do that into any address that we want. So let's start off by talking about the move pattern. The move pattern is a simple pattern made up of two instructions in assembly code. The one being a move from an immediate value stored in a register, and then storing that value in the memory pointed to by another register. So an example would be this, where we have move the contents of EBX register into the memory where EAX points to. And now what we want to do is use setThreadContext API, which controls the registers of a thread, and set the EAX register to point to an address in memory where we want to write a double word, and then write that double word into EBX, and by that we can write a double word wherever we want in memory. The next thing that will happen is we're going to return, which is the next part of this little gadget here we have. And this return, there's a problem with it because we don't know where it's going to return to. And so what we're going to utilize here is something called the jump pattern. And basically we're just going to look for an instruction that is a jump 0, which means it's going to keep executing itself again and again in an infinite loop. It's going to stick the program, and that way we're going to avoid a crash. And so using some tricks that we're not going to cover right now, we're going to get the return to jump to this jump, and everything is covered in this blog post if you're interested. And then this ability enables us to iteratively, one double word at a time, write whatever we want, wherever we want. Now, once we have this write what where ability, you can get creative and think, how can we use this to execute code? In this specific example, the author decided to write a shellcode onto the stack of the target thread, and then using setThreadContext, call virtual protect to change the protection of the page, make it executable, and then run shellcode. Another injection technique that actually we released about a year ago, which was in October of 2016, is called atom bombing, and that uses the global atom table and APCs, which are async procedure calls. Now, we actually witnessed this being used in the wild by Dridex, the notorious banking Trojan. Now, atom bombing works by basically having a malicious process store code in the global atom table. Now, this is done by using the global add atom API. And then what we do here is we have a legitimate process. We issue an APC call or an ASIC procedure call to the legitimate process, and thereby sort of force it to retrieve the code from the atom table and store it in its own memory in a read-write location. At which point we go on to do some return-oriented programming to allocate virtual memory that is executable, copy the memory from the read-write section to the executable memory, and then finally execute the shellcode. Now, all the methods that we've discussed so far, ghostwriting, atom bombing, and the rest, allow you to execute shellcode in a target process. So usually an attacker would want to have their code running inside of a legitimate, very innocent-looking process, which would be either a system-critical process or a process that's used by the user. And so a crash in the code of the malware could significantly impact the system. If it's in a critical Windows process, then a crash could lead to even a blue screen. And then if it's in a user application such as Internet Explorer, then obviously the user is going to notice something. So it would be very nice if there was an ability to create a process that will host our malicious code, and if it crashes, it doesn't affect anything in the system. And that's why process hollowing was invented. Now, the way process hollowing works is that we first create a legitimate process in a suspended state from something such as SVC host. And now what we have is a process that's running in the system, or it's not yet running, but it exists in the system. It will be seen in the task manager, for example. And this process has a process environment block, which points to the main image that is loaded. Now, at this point, it's important to note that we also have the EAX register that points to the entry point of the executable, which means that once the process starts running, this is the first instruction that's going to execute. So what we go on to do is we unmap the main section, the main image, and so we have sort of a hollowed process. And this is where the method gets its name. Now, at this point, we move on to reallocate the memory for our evil.exe. And then we use this memory that we reallocated to write for each section in our malicious code. We write it into the target, into the container process. At which point we can move on to relocate the image if we need to and set the base address in the process environment block if we changed it. In this example, it's not necessary. And finally, we have to change EAX to point to the correct entry point by using setThreadContext. And at this point, all we have left to do is to run the process. And so we resume the thread, and everything works just fine. Now, this technique was useful years ago when it was invented. It was able to bypass a lot of security solutions, but nowadays vendors are aware of it and are able to block it. That being said, let's talk about how. So the most trivial implementations of process hollowing will create an image that is entirely read-write-execute, because it'll allocate everything in one chunk and it won't correct the protection. And this is easy to detect in numerous ways, so we're not going to get into that. But if the malware authors are a bit more creative and they don't just copy the first example off of GitHub, but actually implement it themselves, then they'll unmap the executable and then reallocate with correct protection, for example. In which case, first of all, the unmapping of the main executable is highly suspicious. And also what we need to understand is for every address in Windows, in a process in Windows, we have something called the virtual address descriptor, which is a structure that describes the properties of that address. And the start address of the thread is going to have an image map property, or an image map type, when it's first loaded legitimately. But once the threat actor reallocates the memory by unmapping the main module, the type is going to change, and so we can detect that. Let's say the attackers get even more creative and they decide to, for example, overwrite the original executable without unmapping it, realizing that this change will not be reflected in the virtual address descriptor. So in this case, we need to understand how Windows works when mapping images. When mapping an image, there's an optimization that makes the pages of the image shared, so that if we load it into multiple processes, then the image is shared one time, because we don't want the image to be loaded into every process independently, and thus taking more memory. So when Windows does this, in something called the PFN database, which describes the physical pages of that the operating system is working with, the pages themselves will be marked as shared. Now, once a process tries to write to that page, the page will be turned into a private copy just for that process because it's no longer shared. And this change will be reflected in the PFN database. And so the flag that specifies private or shared will turn from 1 to 0, which means private. And this, again, we can detect. The attacker can get more creative and try to unmap and remap the image. But again, if it's not an executable, then the virtual address descriptor is not going to match. And the best way to do this, to make it look as genuine as possible, is by unmapping and remapping another file as an actual image, in which case, first of all, the start address of the thread is not going to match the address of entry point of the image that's actually loaded, and also the file object that is associated with the process is going to be different from the file object that the virtual address descriptor is pointing to. So process hollowing, not so great anymore given what we just saw. The rest of the techniques we talked about, which are atom bombing, ghost writing, etc., they are missing this file mapping property, right? They create this dynamic code it seems like a runtime generated code, and that's something that modern solutions nowadays are able to detect because it's highly suspicious. So we need something new. Wouldn't it be cool if we could create a sort of a fileless map file? But we know that AVs scan files. So we need to understand how scanners work very well if we want to try to slip something past them. So for that, I'd like to call Eugene to help me out.
So we'll talk a little bit about how the scanners scan the files before they're being executed. Let's consider the generic file execution process. The begin file is opened, and then the section is created out of file, and the memory is mapped into the memory space of the newly created process, and then the execution starts. So various interception can happen. We will cover some places. For example, the file execution can be intercepted during file open process. So usually it's done in the mini filter on the modern Windows during the create file callback. The second place that can be intercepted by antiviruses is the acquire for a synchronization callback, which is called during the section creation before the section is created. And the third place that we will cover today is the process creation notification routine, which is called just before the process starts execution, and it's in its form that allows blocking of the execution is available only for main executable. So before we go further and talk about and see some examples of how antivirus works, let's discuss how what should be done once the execution is intercepted. So antivirus have to scan the file and decide if it's malicious or not. So the scanning can be done either from a user mode or from kernel or from any combination of the two. It's up to AV vendor to decide how to scan the file. And the target file that is being executed should be somehow accessed. So it could be opened by name, it could be opened by file ID on some file system that supports it. And of course, the file object, if it's already available, could be used. The same file object could be used to scan the file. So again, it's up to AV vendor to decide how to access the content of the file. Of course, rescanning the file on each change is not practical. If we would do it, the operating system will be on just scanning files. It would do anything else besides it. So the AV vendor has to decide where to scan the files. So they have some distinct points where they scan the files. If we scan the file before it executes, so it's completely blind for the rest of the techniques that we have talked about. So if the content of the memory is changed or somehow file changed and brought into the memory, it's completely invisible for the file scanning. So let's see some examples of the real stacks taken from well-known vendors. So in the first example, we can see that the execution is blocked during NT-create process just before the file is opened. Here, an antivirus in the mini filter callback blocks the execution. And while it's blocked from the other process, usually it's antivirus process, it tries to scan the file by reopening it. We can see from this example that the file is opened by file name. So the file name was taken from the original operation, and it's used to reopen the file and scan it. The second example is the section creation. So in this specific example, we can see that the Windows Defender, in this case, tries to create a section to scan the file, while other AV vendor blocks it and tries to scan the file before the other scanner do it. And in this case, again, like in the previous case, the operation will be blocked until the file is scanned, and then it will be resumed depending on the content of the file. If it's found malicious, it will be blocked. There's some issue with this specific place. It's called acquire for synchronization because the mini filter API don't allow us to see all the parameters which are passed from the user space. So then we map the section in user space. We have a parameter that tells the Windows kernel that we are mapping an image. And we have another option which specifies the page protection. But inside the AV callback, we have only the page protection, we don't have the image type. Thus, if in the user space we map the image with page read only, for example, the Windows will still map the file as executable, but the antiviruses will see only the page read only page protection, and they might decide not to scan the file because they might think that it's only a data file. It's being mapped. Of course, the Windows loader will never do it, but if the file is manually loaded into the memory for execution, it can happen. And the last place that we would like to cover is the execution. This is not the file scanning. Actually, it's not a file operation. It's actually an execution operation. So here we can see that just after the process was created, the same NT-create process routine was blocked, and the antivirus would go to scan the file exactly as it does in the first example. It's important to know that this specific operation is performed as not as part of file operation. So any subsequent changes to mappings using files will be invisible to this callback. So it's only useful for the main executable because it's in its blocking version. This function is available only for main executable. It cannot be used for dynamic link libraries because it's not available on the older Windows as well. And as I said, it's blind to the subsequent changes to the process using files. So it's not an easy job to create an antivirus. We have to decide where to scan the files, how to scan them. There's always a performance considerations, and antivirus vendors have to support different platforms, different CPU types, different file systems, and this makes the work very, very complicated. But we would like to talk about one more layer of complication that the antivirus have to deal with. It's a transactional NTFS. So transactional NTFS, also known as TXF for short, was introduced in Windows Vista, and it's implemented completely inside the Windows kernel. It works for local NTFS disks. Originally, the Microsoft proposed this solution. They are proposed to use it for multiple file updates that has to be performed as an atomic operation. Either all the changes would be committed to the disk or would be rolled back, depends on the result of the operation. It can be used as part of the larger transaction involving other applications, but it's out of the scope of this talk. And usually this is used for installation processes. You can think of installation that changes a lot of files during the installation process, and then if something happens, files has to be rolled back. Instead of writing a lot of code that rollbacks the files, the installer just can roll back the transaction and every changes would disappear. It's a very nice feature. But just before we continue, these were taken from the Storage Developer Conference back from 2009. You can see that this was a very major change to the kernel code. a large part of NTFS driver was rewritten to support transaction. We have a lot of new functions. We'll talk about them a little bit later. And a lot of functions that were exist previously were changed to support transactions. So we have a really huge change in the specific area of kernel, and it was deprecated. It was deprecated very shortly after it was proposed by Microsoft, and if you look to the MSDN, you just see notice, don't use it anymore. And as usually happens with deprecated features, they're still used. Not used, they're used by Microsoft in stores up to today. The latest Windows update will use transactions. So let's see some API. Before we start, we just have to remind you that transactions have a special function. So the application has to be designed to use transactions. They don't come out of nothing. We have to create transaction using transaction function. We usually end the transaction using transaction commit or rollback, depends on what we want to achieve. For functions in the I/O that works with file names, we have a special function which ends with transacted word, and this function, in addition to the regular options, takes one more option, which is handle to transaction. So we open transaction, then we can access the file by its name inside the transaction, and all other functions which works with file handles will just work also with transactions. So let's see some example. In this example, we create a transaction, we create a file inside the transaction. Let's say it's a new file. We write inside this file and we close the file. So if it would be a regular file, and if you would go to the directory with Microsoft Explorer, we will see this file. But because this file is created inside the transaction, it's completely invisible for the application outside the transaction until we commit the transaction. So only now, when we commit the transaction, the changes can be observed by other applications. At the end, we have to close the transaction handle. So that will continue from here.
So what do we have so far? We talked about history of evasion techniques. We talked about the inner workings of AV scanners and all the different factors to consider when implementing one. We talked about NTFS transactions, and you must be wondering what's next. Well, naturally, transactions make life very hard for AV vendors. Now, what we want to do is we want to leverage this and try to create a process from a transacted file. That being said, the Windows loader, as most of us know, the Windows process loader only accepts a file path to create a process. And we don't have an API create process transacted. So what we're going to do is we're going to try to dive into the process creation process on Windows and try to see if we can find a way to somehow create a process out of a transacted file. So comparing the create process function between Windows XP and Windows 10, superficially we get the impression that Microsoft changed completely how processes are created. But if you look deeper into it, then you see that Microsoft moved most of the code from the user mode library kernel 32 to the NT kernel itself, and somehow the function in kernel 32 became longer. Logically, the steps remain mostly the same, but let's take a look at the process loader on Windows XP. Now, we're going to take a look at this in assembly code, but for those of you who don't know assembly, it's okay. The words are pretty clear, and I'm going to explain every step as we go along. So as we can see, the first step is we call an internal routine, which goes on to open the file. So we open the file here with a few permissions that we're asking for the file, and if that fails, then we try to open the file again with less permissions, which is, I guess, something that all of us do in our code sometimes. At this point, we create a section. A section is an object that can be later mapped into memory. Now, the thing to note here is that the type of allocation is sec_image, while the page protection is page execute. Now, as Eugene said before, this is how the Windows loader does it, but nothing prevents an attacker from passing a parameter of section page protection of page read only, which could cause the antivirus to skip the scan altogether. At this point, we call the kernel to create the process object, to create the new process. Now, the thing to note here is that we use the section handle that we opened before. So the steps are we create the file, we create the section, and then we create the process from the section. So the file has already been opened at this point. Now, the kernel, what it does is creates the process object using the create object routine of the object manager, and then adds the process to the list of running processes. At this point, we move on to talk about something called the process parameters. Now, process parameters are a structure that every process has on Windows, and it's crucial for the ability of a process to run. Without this, the process cannot run. And it contains stuff like the command line of the process and that kind of thing. Now, at this point on Windows XP, we can see that we have a subroutine called base push process parameters, which what it does is it creates the process parameters, allocates memory in the new process for the parameters, copies the parameters to the target process, to the newly created process, and then finally sets the address of the parameters in the process environment block. Now, the important thing to note here is this happens after the process is created, and it's implemented entirely in user mode. And we'll see why this is different in just a second when we take a look at Windows 10. At this point, we create the thread for the process, the main thread, and if the flags specify it, we resume the execution of the thread. And that's it for Windows XP. Now, if we compare this to Windows 10, we still have the same subroutine that's inside, and we can note that the first thing that happens here is that the first function that's called is base create process parameters, which creates the parameters. We can see the parameters being created and filled out with some data. But this happens before opening the file, before creating the section, before a process even exists. At this point, we call this new system call. It's not that new. It was introduced in Windows Vista. But it's this system call called NT-create user process does not accept a section handle like the one in Windows XP did. It actually expects a file path, and the kernel opens the path for us. The other thing to note here is that the process parameters are being passed to the kernel, as opposed to Windows XP when this was copied post-process creation in the user space code. So if we take a look at the kernel routine, we can see that we try to open the file in kernel, as opposed to Windows XP when it was a user mode. If it fails, then we try again, of course. Then we create the section, just like in Windows XP, except now it's happening in kernel. At this point, we copy the process parameters from user mode to kernel mode. And then we move on to call the allocate process routine, which, again, calls the create object routine to create the actual process object, allocates virtual memory for the process parameters, copies the parameters to the new process, and then sets the value in the process environment block. From this point on, there's not much left. We are allocating the main thread. We insert the process and the thread into the respective lists. At this point, the process create notify routine that Eugene mentioned earlier is called. And we leave the kernel. And if we need to, we resume the thread according to the creation flag specified. Okay. So, to highlight the main differences, in Windows 10, we have NT-create user process being used instead of NT-create process EX. Now, NT-create process EX receives a handle to a section, while NT-create user process receives a file path. Luckily for us, NT-create process EX is still available in the latest Windows 10 release because it's used in the creation of minimal processes, which is a bit beyond the scope of this talk. Now, the only thing is, unfortunately, all the supporting user mode code that we had in XP is no longer available for us. So what we need to do is we need to implement the heavy lifting on our own, by ourselves, by creating it ourselves. Let's talk about doppelganging. So our goal here is to load and execute an arbitrary executable inside the context of a legitimate process. And we want to use none of the suspicious process hollowing API calls, such as unmap view of section, virtual protect, set thread context, APCs, and that kind of thing. We want AVs to scan only clean files or to not even scan us at all. And we don't want to be discovered by advanced forensics tools. So we break doppelganging into 4 steps. Step number 1, transact. Step number 2, load. Step number 3, rollback. And step number 4, animate, which brings the doppelganger to life. Let's take a look at step number 1, transact. First off, we create a transaction, just in the example that Eugene showed before with a simple transaction-aware application. At this point, we open a file that is a legitimate file, such as SVC host, inside of a transaction. So we have a nice, green, clean-looking file object that we just opened, and it's opened inside of a transaction. What we're going to do now is we're going to overwrite the file inside of a transaction, and now it's tainted with malicious code. The only thing to note here is that anyone looking at this file from the outside doesn't see our changes. They're reflected only within the context of the transaction context. Step number 2, load. What we do at this point is we create a memory section from the tainted file. And so we have a newly allocated section object that contains all the malicious code that we wrote to the file. At this point, we can move on to rollback, which is, as we talked about before, when you're working with transactions, when you're done, you need to decide if you want to commit the transaction and save the files to the disk, or if you want to roll them back because you ran into some kind of error. In our example, we have no interest in committing the transaction because we don't want anybody to see the changes we made to the file. So what we're going to do here is we're going to roll back the transaction. The file becomes green again and clean. And this really effectively removes all of our writes from the file system. Now, we move on to step number 4, animate. Using the details we found out before from examining the Windows process loader, we can call the ntcreate process ex routine that was used in Windows XP to create a process from the section that we created. And so once we do that, we now have a green process, a nice clean looking process that's running or hosting our malicious section. At this point, we create the thread of for the main thread, and we move on to do all the heavy lifting that we need to do that Windows XP's user time libraries used to do for us, which is to create the process parameters, to fill them out with the correct parameters, to allocate memory for the parameters, to copy it into the Doppelganger process, and then to set it in the PB of the Doppelganger. And then finally, all that's left to do is resume the execution, run the process. And now we have a nice green process that's running, and the AVs will not take a look at it. So let's see this live in a demo. I have here a virtual machine that, as you can see, it's running Windows Defender on the very updated definitions, December 7th, that's today. And what I'm going to do here is, we have this password dumping tool that should be well known to everyone. And while we don't really think this is a hacking tool on our own or on its own, Windows Defender seems to think so. So let's try to double click it and see what happens. Virus and threat protection, threats found. So Windows Defender found threats. Obviously, the executable did not run. Now, what we're going to try to do is we're going to create a doppelganger of MS Paint, which is the Windows utility for making nice little drawings. And we're going to have this actually execute the same tool, except this time it's going to read the tool from disk in an encrypted form so that Defender cannot scan it. And let's see if Defender has any problems with this action. At this point, the tool was executed. This is a fully functional tool. It can be used, and as you can see, Windows Defender doesn't seem to mind. Process Explorer can help us take a look at what's going on here. Maybe we can figure out. If we take a look and take a look at the process, we can see that we have MS Paint running, and there's nothing here showing us that it's actually a different tool that's being hosted inside this process. It actually even preserved the icon, which is really interesting. If we even try to verify, it'll say that this is verified. So that's really nice. Thank you. So while conducting this research, the first time we ran this thing on Windows 7, and it worked just fine. And then we ran it on Windows 10, and the system crashed. And so it turns out that there's a bug that was introduced in Windows Redstone and reported by James Pershaw. And it's a null pointer to reference, so nt-create process ex, when it receives a 0, is one of the parameters. It tries to dereference it without checking first, and so the system crashes for an access violation. And luckily for us, though, Microsoft was nice enough to fix it for this talk, because the bug was introduced in Redstone a while back and fixed in the False Creators update 2 months ago. So if this lecture was taking place 2 months ago, we couldn't do it on the most recent Windows 10 release, but now we can, so thanks. The affected products of process doppelganging are the following that we tested. We tested all these. They were all bypassed. What we did is we took the executable, such as the tool we showed before. We saw that the antivirus flags this as an executable. When we double click it, then we loaded it as a doppelganger, and it was able to run with no problems. If we want to talk detection and prevention, then first of all, it's not so easy, but a simple way to go about this is to scan the file object available in the create process notification routine and to use the exact object, not to reopen the file. And if you get an error while trying to do it, then you know doppelganging is taking place, so you should block it. About DLL files, this doesn't help. So what you can do here is try to scan all sections, even data sections, because as we saw, the flags in the minifilter callback are actually misleading. As for forensics, if you want to detect a process in retrospect that has been doppelganged, you can take a look at the file object of the associated with the process, and if it has the right access enabled, then you can know that something fishy is going on here, and there's a good chance it's process doppelganging. And also, specifically on Windows 10, the eProcess structure has something called the image file pointer, which is supposed to point to the file object, and this will be null in a doppelgang process. To sum up, process doppelganging allows us to take a malicious executable, load it in the context of a legitimate looking file, and create a process out of it. We use the Windows loader, right? So there's no need for a custom reflective loader of any sort. The file is mapped to an image file correctly on disk, just like any legit process. And we don't have any of the unmapped, dynamically generated runtime code that is usually associated with modern malware and is detected by modern solutions. This can be leveraged to doppelgang DLL files as well, and it's completely fileless. And even advanced forensics tools such as volatility won't detect it at this point. This works on all Windows versions starting Vista and bypasses all these solutions that we tested, the security solutions. We'd like to give a special thanks to Omri Misgav and Udi Avo, who helped us a lot with this research, and without them it wouldn't be possible, so thank you guys. And thank you all for coming and listening, and at this point, if you have any questions, we'd love to address them.
All right. What are the questions that you would like to ask them?
Thank you for the talk. I have one question just to double check if I understand it correctly. With this technique, when you execute the malicious code, it will have all the privileges the process you're using for that will normally have, right? So for example, if that was the MS Paint and I'm executing my malicious code, it will be able to do anything which the MS Paint process would be able to do. Is that correct?
Yeah, it's running with like MS Paint. The process gets the token just like MS Paint, but it all depends in Windows on the context on which the process was created. So if it was created by an unprivileged process, then it won't have privileges. If it was created by a privileged process, then it could do anything.
Thank you.
Next question.
Thanks for presentation. I just have one question. Did you guys investigated this transactions API that you used on Windows? Does it have any kind of memory implications? So where you created file and transaction should be created somewhere, right? So maybe these implications are detectable.
Okay, so that is they're actually written to to the file system in special files, and the details of this can be read about online on MSDN. It's documented.
Hello. My question is, what about access rights? Are the rights checked just after committing or at the beginning of the create transacted file? Can you spoof also a process that is unavailable to you?
No, I don't follow, sorry.
The binary, there was an example about svchost.exe.
Yes.
What if it's a protected process that's unavailable to, for example, you don't have rights to read it?
Oh, so you mean on the file system level, I don't have access to it, so no, if I can't open the file, then I can't do anything to it.
Yeah.
But in theory, I could just copy the file somewhere and then do it from there.
Okay, thanks.
Anyone else has a question?
Thanks for the talk. What about code signing and executive signings, like certificates for executables? Sorry.
So as we saw in the demo, if you took a look in Process Explorer, for example, which tries to verify the digital signature of the process that's being executed, so it looks legitimate. But if you take a look in memory at what's running, if you investigate this at runtime, then obviously you'll be able to tell that something happened. So the signature will not match.
We still have time if you have any other questions.
Thank you for your lecture. One question about, does the app locker prevent this? Does the app locker check the memory contents or does verify on the disk?
So that's a good question, and I actually am not sure about that because we didn't take a look at AppLocker in this research. We mostly focused on bypassing security solutions by seeing that they incorrectly handle transactions. So I don't have the answer for that.
Next question. We still have 10 minutes.
I was wondering, have you gotten any response on this from Microsoft? Will it be patched somehow?
So we've actually disclosed this to Microsoft, and they didn't deem it as a vulnerability, which it's not. The operating system is behaving as it should. The only thing here, maybe that they could change is to add to, in the minute filter callback, you could tell the antivirus that a section is being created for execution, even when you can kind of fool it into skipping that. But other than that, there's not much Microsoft could or should be doing. It's the antiviruses who should handle transaction correctly.
Thank you.
So to that point about Microsoft not considering this vulnerability, are there legitimate cases where you would use transactions here for creating executables? So
that shouldn't happen, because as we saw the Windows process loader, the official exported API, it only accepts file paths. There's no way to run a file out of a transaction. It's only using the system calls directly that enables us to create a process from a handle. We take the handle to a file, we create a section, then from the section we create the process, but that is something that the Windows loader is in charge of doing. And as you saw in Windows 10, this no longer even happens in user mode, it happens in kernel mode. It's just that the old system call is still available.
Okay, so then the real question is, why do they persist that old method?
Why does it still exist?
Yeah.
So it's a bit beyond this scope, but the general idea is that NT-create user process creates a Windows process, while NT-create process is just a relatively much thinner wrapper around the function that creates the object of a process. And so it can be used to create a minimal process, which doesn't have a lot of things that a normal process does. And it can be used in running things like other subsystems on Windows, such as, for example, the WSL, the Windows system over Linux, which can be used to create these types of processes, which are not normal Windows processes.
Thank you.
Next question.
So this is a follow-up question of a question that was asked before. So they asked you for a reaction from Microsoft, but did you get also some reaction from the antivirus software companies?
Yeah, so antivirus software companies have been aware of this issue. It's online. If you look up antivirus plus transactions, you'll see that it's a known fact that they don't handle transactions correctly. They're aware of this issue. They just haven't taken care of it yet. And that's what we're trying to show here, is that even 11 years after this feature was introduced, fully documented, and people have discussed online that antiviruses don't handle transactions well, still 11 years later, and all the antiviruses can be bypassed using this technique.
Does anyone else has a question?
Thanks for a good talk. I was wondering if this could be used in a way with executables which elevate automatically, which are signed by Microsoft. So say you pass the parameter of a process, well, for example, in your example, you pass a parameter for a executable that you want to elevate, and you said it inherits is it the security descriptor of the process which the host process? So could that be used for like process elevation or?
Yeah, so you're talking about auto-elevating processes, right? Yeah, that's a very good question, and it's something that actually we've dealt with in the past. You can see on Breaking Malware on our blog, we actually did some UAC bypasses using exactly what we did specifically is we used an auto-elevating process, and we changed the environment for it so it loads our DLL. But so this could actually be potentially used for this, but we haven't gotten around to testing that yet. But it's on our to-do list.
All right, thank you.
If you still have a question, we still have time. I guess. Yeah, you still have time, guys, yeah?
Yeah, we're done. Thank you. Thank you, guys.